So non-permissible values exist when you have variables in your denominator, or a letter appears in your denominator, correct? Because your denominator is not allowed to equal what? 0. We got there. All right. So in this case, we do have tan x. So we have tan x can't equal 0. Because wherever tan x would equal 0, I would replace that denominator with 0 and it would be kicked out. Correct? It wouldn't work. So where does tan equal 0? Tan, another way to look at it, which makes it easier, is switching tan to sine over cos. So I could write this as 1 over sine x over cos x. And then both of these are sitting in the denominator, correct? So I can either say where tan x can't equal 0, or where sine x and cos x can't equal 0. And both of those places are where tan can't equal 0, because tan is undefined at 90 and 270, and it's 0 at 0 and 180 and 360. So if I draw the spots where sine x is equal to 0, where y is equal to 0, it's here and here. If I draw the spots where cos is equal to 0, it's here and here. So I could give two general solution non-permissible values. I could. Or I could just give these all together. How could I write this as one non-permissible value, general solution, if it's at all those spots? Yeah, so do we need the 0? So we could just go 0, but not write it, plus 90 degrees N, NEI. So glad it's the blue box. So example 2 says determine the restrictions, same thing as non-permissible values, on the variable for this equation now. So what is sitting in my denominator? A cos x and a sin x, and this one just has a 1, correct? So once again, we have to do where cos x can't equal 0, and where sin x can't equal 0. We already did that in the previous question, didn't we? So are the non-permissible values going to be the same as the previous question, even though the question is different? Yes, they still result in the same issues. So we can write it again as x can't equal 90 degrees N, NEI. I'm just picking degrees because it didn't specify. If it says radians or it says degrees, you'd have to do what it says. So this one didn't give me any restricted domains, correct? So that's why I have to give general solution MPVs. The other option they could give me is 3. Determine all non-permissible values in the interval 0 to pi. So now I'm not going to give general solution. I'm just giving the spots where it exists between 0 and 2 pi, so on this unit circle. What we have is cotan x over 1 plus cos x. Now what I'm going to do is I will always change tans, cosecants, secants, cotans to coses and sines because it's easier. So if I look at the numerator, it's cotan x. So I can rewrite that as cos x over sin x all over 1 plus cos x. So what are my denominator issues? 1 plus cos x. 1 plus cos x can't equal 0. There's also another denominator, sin x. It's still a denominator even if it's in the numerator. Because I could write this out sideways. I could go cos x over sin x divided by 1 plus cos x over 1. Anything on this side is divided by, and that's divided by. Do you see that? So that's why all of them count. Okay. So my other one is sin x can't equal 0. So let's find the spots where these equal. We could always state the answers separately for both. But what we can do is also see if maybe some of them overlap. Okay? So this one I'd subtract my 1 over, and I would say cos x can't equal negative 1. Well, where does cos x equal negative 1? Where x equals negative 1, which is here. We agree? It doesn't say plus or minus 1. We didn't take the square root of 1 or anything. We just moved the 1 over. So it's where negative 1 exists. Yes?
Yeah.
Okay. Then we need where sine x can't equal 0. So where does sine equal 0? 0 and pi and 2 pi. So what's the catch with these two? They actually, not contradict, they actually overlap. Same thing, work as well. So this answer to this one, if I make it red and I draw it on here, is actually covered by that one already, isn't it? So do I have to say it twice? No. The other thing we have to look at is this is 0 to 2 pi square brackets, so it's inclusive. So we'd say x can't equal 0, pi, 2 pi. I did not give a general solution because they gave me a restricted domain. So if I'm not given a restricted domain, I state general solution, non-permissible values. If I'm given a restricted domain, I just state where those exist within that domain. Pardon? That's okay. All right. This one, we have sine x over 1 plus cos x, 1 plus cos x sitting in my denominator over here. So I'm going to have to use that for my restrictions. Equals tan x. What can I replace tan x with? Sine x over cos x. So I have sine x 1 plus cos x equals, oops, sine x over cos x. This isn't a really good proof. It's actually wrong. That's okay. All right. So now we have two different denominators. We have 1 plus cos x and we have cos x. We agree? So we're going to go 1 plus cos x can't equal 0. And then we're going to do cos x can't equal 0. Does this one have a restricted domain on it at all? No, so we're going to have to give general solutions, correct? All right, where does this one, cos x equals or can't equal -1? So where does it equal -1? At that 180 or pi, depending on if it's radian degrees. Where does cos x equal 0? 90 and 270. Can I lump these together? No. Because if I did 90 n NEI, I would actually get this arm as well, and that's not a solution, correct? On either of them. So I have to do them separately. I have to say x can't equal, I'm going to do this in radians. So this is pi plus 2 pi n NEI, because it has to go around in a full circle. This one is pi over 2 and 3 pi over 2, so it's pi apart. So this one I have to go x can't equal pi over 2 plus pi n NEI. And I would have to give two general solutions. I can't give it as one. Yeah?
The first solution equals or not equals?
Yeah. If they ask what the restrictions are equal to, then it would be equal to. But if you're just stating restrictions, you say they're not equal. Speak.
Why is it 2 pi after you just said it can't? You just said it's not 360.
This is plus 2 pi. So it starts at the pi, and then when I add 2 pi, that makes it land back on it again. So it is not actually 2 pi, because doing a whole 2 pi on above this will keep going and not touch that. Does that make sense? Okay, flip over. Okay, so these ones want me to simplify, this one wants me to simplify it and state restrictions, right, Campbell?
Right.
Right. So we're going to simplify and state restrictions. So this one here is, he was not being Crystal at the time, he was being Campbell. Sine squared x over cos x, I went there, plus cos x, technically over 1, right? Are they all sines and coses? Yeah. If they're like cotans or tans or secants or cosecants, you might want to change them before you state non-permissible values. But these are all nice sines and coses, correct? The only thing I have in my denominator is cosex and a 1. So I'm going to do my restrictions first. My restrictions are where cos x can equal 0 and cos x equals 0 here and here. I'll do it in degrees. So it's going to be x can equal 90 degrees plus 180 degrees and NEI. Okay, it wants me to simplify this. When I have a partial fraction plus another fraction, what do I have to do? Yeah, common denominator. I need to get them to actually be the same so I can put them together as 1. So I'm going to multiply this by cos x so that I get a cos x in my denominator. Then I'm going to multiply this by cos x as well. So this is going to equal sine squared x over cos x plus cos squared x over cos x. Which equals sine squared x plus cos squared x. Cos times cos. I didn't rationalize the denominator, made a common denominator. Sine squared x plus cos squared x. What is sine squared x plus cos squared x? 1. So it's 1 over cos x. What can I write that as? Secant, someone said. You are right. Six, 7, and 8. Wow. 9, 10. Go. So this one, we have 1 minus cos squared x over sine x, which I've told you numerous times. You have to rewrite the question. You can't start working it down without the question. You didn't write that. They typed that. So you have to write it out. And then you get sine squared x over sine x. And then I see that a sine can cancel off because it's a monomial and monomial, right? But I have to state restrictions before I cancel. You were taught that in rationals in 20-1. Because if at any point in time it was a non-permissible value, it still counts. So always say before you cancel. So I'm going to have sine x can equal 0, which is here and here. So x can equal 180 degrees n and EI. And then the squared cancels off one of these signs. And if that doesn't make sense to you, sine squared x alone by itself is the same as sine x times sine x. So I could write it out twice that way instead, and then just cancel it off completely. And then I'm still left with the sine x. Example 7. Guys, you're going to have no review tomorrow. I'm going to kick you out. You guys won't get to have it. It's going to be really sad. Be a party and you won't be invited to the review party. All right. Tan x over secant x. Tan x is sine x over cos x divided by 1 over cos x. So a lot of people think the 1 isn't actually in the denominator. The 1 and the cos x are in the denominator, correct? The 1 and the cos x. So if I had like something else down here instead of the 1, I would have to state restrictions for this, this, and this, because this is full denominator, correct? If it makes no sense, you can write it this way. Sine x over cos x divided by 1 over cos x. So you always state everything but the top left. Remember that? You were taught that in rationals last year as well. Because this cos x is in the denominator, and then the 1 will be in the denominator when we flip it. Do you You can either write it sideways and cancel it off, or you can leave it stacked and cancel them both off because they're both in the denominator, right? Before I canceled them off, though, what should I do? State restriction. So I have where cos x can't equal 0, which is here and here. So x can't equal 90 degrees plus 180 degrees n. Anyhow. And my answer is just sin x. All right, the next one wants us to prove and state non-permissible values. I've made you just prove, correct? But you do still have to state non-permissible values as well, if it's asked. If I just ask you to prove an identity, you just prove it. If I ask for non-permissible values and proof, then you have to give me the non-permissible values. So this one has a left side and a right side because I'm proving LSRS 1 minus cos squared x over sin x equals sin x. So what is my only denominator here? Sin x. So my restrictions are going to be sin x can't equal 0. And that's here and here. So it's x can't equal, if we do it in radians, pi n nei. Does anyone know anything I could do here? It's a really easy proof. If you got this one, you should have. Yeah. Yep. 9 and 10, go. Tan x. Did you rewrite the question first? Please tell me yes. And if you didn't, do it. All right. So tan, we switch to sine over cos, sine x over cos x. All over, what is 1 plus tan squared the same as? Secant squared. He's back, it's fine. So we get sine x over cos x divided by 1 over cos squared x. Now, this denominator is a cos x, this denominator is a cos x and a cos x. So that's just the same thing though, right? So this is going to end up canceling this off. But before I cancel, I have to? Yeah, NPVs. So I'm going to say cos x can't equal 0. Do not freeze. Cos x equals 0 here and here. X can't equal 90 degrees plus 180 degrees and NER. NER. NEI. All right. This squared can cancel off this one. But now I'm left with sine x over 1 divided by 1 over cos x. What could I do instead of dividing by 1 over cos x? Multiply by cos x over 1. And at this point, my grandma would not know those are the same. She's a genius, but still wouldn't. So I have to go sine x, cos x. And now she would know they're the same. Grammy Hammy. All right. Okay, conjugates. Listening. 1 plus sine x, 1 plus cos x. Yes? Those are answers, bless you, to a difference of squares. We agree? So if we look here at this one, we still need to prove. So our first step is going to be rewrite it. I'm going to get sine x over 1 plus cos x, and then plus sine x over 1 minus cos x, which is conjugates, equals 2 sine x over 1 minus cos squared x. And you have to stop yourself. Even if you see 1 minus cos squared x in difference of squares, you can't do that. Okay? Because the first step is to rewrite it. All right. So I need to go 1 plus cos x can't equal 0. 1 minus cos x can't equal 0. And some people don't realize that that's actually the same as 1 minus cos squared x, so they'll also set this one equal, not equal to 0. Let's solve them up. So this one's going to be cos x can't equal -1. This one's going to be cos x, because I'll just move the cos x over, can't equal 1. This one I'm going to subtract my 1 over or add my cos squared over. So I'm going to go 1 equals cos squared x. Then I have to take the square root. When I do the square root, what do I have to remember? Plus or minus. So it's going to be plus or minus 1 equals cos x. So this encompasses both of these. It's the same thing, correct? So we really just want where x is equal to 0 and 1, or sorry, -1 and 1, which is here and here. So it's going to be x can equal 180 degrees n NEI, or pi n NEI, because I didn't specify it as radians or degrees. Okay. The left-hand side is a fraction plus a fraction. When you add fractions, what do you need? Common denominators. Now this is the catch. You can't make a binomial be another binomial. Like I can't just add a cos x to this or subtract a cos x from this and make them the same. So to make them common denominators, you actually have to multiply them by each other. So I'm going to multiply this one by 1 plus cos x. 1 plus cos x. And this one by 1 minus cos x. And so I'm going to get, distribute the top, sine x minus sine x cos x plus sine x plus sine x cos x all over 2 conjugates multiplied. What do 2 conjugates multiplied give me? Difference of squares. So I'm going to get 1 minus cos x plus cos x, those cancel, minus cos squared x. So I'm getting minus, no, not the time. Do not freeze. I'm just about done. Anger level rising, because it's going to just evaporate soon. It just goes away. Okay, anyways, we're just going to talk it out before it evaporates. So I get 1 minus cos squared x, which matches that one. Then minus sine x cos x plus sine x cos x cancel off. And what's sine x plus sine x? 2 sine x. And on the bottom, you're going to have 1 minus cos squared x, so they'll match. Yes? Before this evaporates? So the negative sine x cos x and the 1 sine x cos x cancel each other off. And then I get sine x plus sine x, which is 2 sine x on this left side. There, see, it went away. And then minus cos squared x. I don't know why it does what it does, and I don't know why it hates me. But they will match. Does that make sense? All right.